So batch normalization is another very, very interesting idea in deep learning, which I think was discovered around 2015, if I'm not wrong, probably late 2014, early 2015. It's a very interesting idea. So let me explain you the problem that we have with deep networks and what problem does batch normalization solve. First thing, remember, remember I have a network like this. Let's assume this is layer one, right? Fully connected, and this is layer two. And let's assume this is my output, right? This is my y hat. Let's assume I have an x that this is my input. This is my input. This is my output, right? And this is my x, right? I have a bunch of neurons here. I have a bunch of neurons here. Instead of drawing that big diagram that I always draw, I'm writing a shorter diagram. Of course, there are a bunch of neurons here. They're fully connected. Let's assume this is a fully connected. This is a fully connected MLP. This is a fully connected multi-layered perceptron. Let's just say. Now, the first thing that we will do, that we always do for any optimization problem is, given our data set of xi's and yi's, right? As a pre-processing step, we normalize, we perform data normalization. We perform data normalization on xi's. By data normalization, what I mean here is mean centering. What I mean is mean centering and variance scaling. Okay, what does it mean? It means I take each of my xi's and I modify my xi's. Let me call it xi tilde as xi minus mu by sigma, right? Where mu is the mean of, it's a mean vector, mean of all xi's, and sigma is the standard deviation, of all my xi's, right? This is your data normalization. This is something that we learned long ago when we learned about logistic regression and things like that. And we also understood why data normalization is required, right? So that the weights are interpretable and all of those things, right? So that the weights make sense, all of those things, right? Now, of course, at the input level, so all these neurons, whatever input we give, right? So let's assume there are some 4 neurons here, some 2 neurons here. So all these neurons, whenever they get an input, that input is normalized. That input is data normalized. But what might happen here is, imagine a network which is very deep. Let's assume this is my input. This is my layer 1. Okay, let me not put it as then layer 2, then layer 3, then layer 4, then layer 5, then my output layer, right, which generates my y hat. Let's assume I have a deep network like this. Let's assume this is also an MLP which is fully connected. Let's just say, lots of layers, not just 2 layers like this, but lots of layers. Now what happens is, let's assume in this layer we have some inputs, some more activation units, etc. What happens here is, if this input changes slightly, remember our input is a mini batch. Because we're employing mini batch based SGD techniques, right? We do not send the whole data as the input, right? We may send one point or a small set of points. So let's assume we are operating in the mini batch world, right? So between batches, so if this is my total data, let's assume this is my total data. I'm breaking it up into batches. In the first iteration, I send this batch. In iteration 1. In iteration 2, I send this batch. In iteration 3, I send this batch. In iteration 4, I send this batch. Iteration 5, I send this batch. Iteration 6, I send this batch. That finishes my whole epoch. Again, I repeat. Iteration 1, iteration 2, so on and so forth. Okay, again, this batch, so on and so forth, right? So if my input even changes slightly, because I have lot of layers, right? And each layer is doing some multiplications, additions, and transformations. A small change in the input can lead to a large change. In the later layers, especially if you have a deep neural network. Especially, let's assume you have 5 hidden layers. A small change in input can lead to a large change. The reason being that this small input is getting multiplied with lots of weights, and then it will go into exponential function if you're using sigmoidal, or there are lots of operations that are happening on that small input. right? So for example, let me show you an example how small input, small changes can have large changes. So let's assume I have two variables, 1 and 1.01. Let's assume in the next step I just multiply it with itself. So I get 1. Next step I multiply this with itself, right? What is 1.01 square? Right, 1.01 into 1.01, that is 1.021, right? Okay, so that is 1.02, sorry, let me check it again, 1.0201. Again, I multiply this with itself, again 1, I multiply this again with itself. Okay, so let's actually take it as 1.0201, sorry, 1.0201 squared. Okay, what happens now? I get 1.04. Okay, sorry, I get 1.04, 0406. If I keep doing this a bunch of times, this will remain 1, but this value can increase dramatically. For example, if I keep doing this, let's say 5 times. Okay, so let's actually write it down. Okay, so if I keep doing this squaring 5 times, okay, sorry, so let me type it. So if I keep squaring it up, because I'm multiplying it with itself, right? So if I do it a few times, I get 375. So I get 1.375. This number is the same, but this has changed. This is 37% more than this, right? By just applying a very simple operation a few times. The operation here is I multiply it with itself. I multiply it with itself. I multiply this with itself, right? And here the operations you have are far more complex, right? Because if you're using a sigmoidal unit or even a ReLU, right? You're multiplying with lots of weights, right? And you're summing them up. You're passing them through a ReLU unit or a sigmoid unit. Again, you're taking the output here, passing it through the next layer. So a small change. So here this change is very small. Here the change is only 1%, right? Because the difference between 1 and 1.01 is only 1%. But you repeat this operation a few times, the change here is 37%, 37.5%, just within a few steps. So what happens is a small change in the input or anywhere can lead to a large change deep in the network. And large changes, imagine look at it from a neuron in L5's perspective. Okay, let's look at it. So let's look at the world from, so you have X, you have L1, L2, L3, L4, L5, output and Y hat, right? So let's take a neuron in L1. The input, the input that it gets in each batch. So I get a batch input, right? I get a batch input to this. Basically a set of exercise, right? Which is what I call my mini batch. There is very little change in the inputs because at the start itself, you've done mean centering and variance scaling. You've done this, right? So between each batch, because you've done the scaling and centering, you've done data normalization here, right? Between each batch, a neuron which is there in L1, a neuron that is in L1, does not see huge difference. It sees a small difference from one batch to other batch. But take a neuron which is at L5. Because there are a lot of operations that are happening between, let's say, batch 1 and batch 2, it sees a huge difference in the distribution of points that it sees. Because what does a neuron at L5 see? It sees outputs from L4. And because there are so many operations, even though there is only a small change between two batches at L1, right? Because it is passing through these many layers, a neuron which is at L5 will see batches being very, very dissimilar, which means the data is not normalized. Because look at it, each of this can be thought of as a model, right? For every model, ideally you want your data to be normalized. But the problem is because you have these many layers, even though at the input level everything is well normalized, because you have these many layers, a neuron which is at a very deep layer starts to notice that between one batch and other batch, the distribution is very, very different, right? Ideally, what do we want? We want all our inputs to be mean centered. We want them to have a mean of 0 and a variance of 1. Right? This is what mean centering and variance scaling means. Right? This is what data normalization means. This is the distribution of inputs that I want to see. But what happens is for this layer, In batch 1, I might see a distribution like this. In batch 2, I might see a distribution like this. In batch 3, I might see a different distribution like this. And as the distributions change, and they may not even be normal, by the way, they may not even be Gaussian. As the distributions change, the neuron which is there in this layer can go crazy, because every time it's seeing a different input or different distribution of inputs, right? So this is a problem. This problem is called internal covariance shift. This problem is called internal covariance shift. Very simple. It's internal because within the network you're seeing this problem. Covariance is basically a generalization of variance to multiple variables, to a vector, right? Instead of your input being a scalar, if it's a vector, you can compute its covariance. And the covariance shifts. Here the variance is shifting and the mean is also shifting. Here there is a covariance shift. This problem is called internal covariance shift. So the solution for it is also very simple. The solution for it is this. If this is my input, layer 1, layer 2, layer 3, layer 4, layer 5, output and y hat. Right? The idea is very, very simple. The idea is, suppose if I get batch 1 here, followed by batch 2, followed by batch 3, I can add a new layer here. I will add a new layer here. Okay, let me erase this and put it there. Right? So what it says here is, I will add a layer called batch normalization layer. It's a new layer. What I do in the batch normalization layer is, whenever I get a batch of inputs, okay, as the name suggests, this is a batch normalization layer. Whenever I get a batch of inputs, I normalize just that batch. Okay, now what happens if I normalize this batch? Suppose if I have a neuron in L5, because I'm performing batch normalization, because what does batch normalization mean? Take the batch of points. Let's assume I have a batch of points. Let's say x1, x2, so on, xk. Okay. I normalize I do simple data normalization on just this batch, not the whole data set, just this batch. For every batch, I normalize it. When I do normalization on every batch, what happens? If I see one batch having this distribution of inputs, the next batch, because I'm normalizing it with 0 mean and 1 variance, because I'm normalizing every batch that comes, the second batch also will have the same distribution. The third batch also will have the same distribution, because I'm explicitly normalizing each batch of inputs. Remember, not the whole data, but just that batch. So batch normalization, you can think of it as an additional layer that you're adding, especially deep in the network. Of course, you can add a batch normalization layer here, batch normalization layer here, etc. But batch normalization works very well deep in the network. Right? Deep in the network, where small changes here can lead to large changes. If you add batch normalization, all the distributions again do not have this problem. You have a much better world where the inputs that any neuron deep in the network sees are all coming from the same distribution, which means it can train better. Right? It can train much better. Now, let's look in the reference section of this chapter. For this video, I've given you a link to a research paper, the original research paper which discusses how batch normalization should be done. Right? This is the original research paper from 2015. Right? So let's assume I have a mini batch B of m points. Right? So here I have my batch normalization layer. So here it's defining what a batch normalization layer does. Right? Suppose this is my batch normalization layer. It has some input. It has to generate an output. Right? Just this input. So this is not this x and this y. It's not that. It is just the x and y which are input to this layer and output to this layer. That's what we're talking about. That's what this notation explains. Right? Suppose I have x1, x2, xm, a batch of points, batch of m points. Right? A batch normalization layer has two parameters called gamma and beta. Right? And given an input, so let's look at it. Let me draw it carefully here, slightly in a better way. So my batch normalization layer is here. My batch normalization layer gets a batch of inputs. Let's call this batch B. It generates y. This batch contains xi's. It generates yi's. Okay? It generates yi's. So it basically transforms. Actually, I don't like this terminology yi. So let me just change it here. Okay, let's assume it generates yi tildes. Sorry, xi tildes. So your input a batch, it outputs a batch. Let's call that batch as B tilde. Okay, batch normalization has two parameters, gamma and beta. Let's understand what it does. Okay, so instead of yi here, I prefer to call it as xi tilde. Instead of yi here, I'll call it as xi tilde. Okay, because I really don't like you confusing you with notation. That's the worst thing. Once you're confused with notation, everything goes down the dustbin, right? So let me call it as xi tilde. Now, first, given this batch, you're computing the mean of the batch. This is like simply computing the mini batch mean. You're computing the variance of the batch. And for every point xi now, which is there in the batch, you subtract the mean and you divide it by variance. But you're adding a small value here, sigma, because if your variance is 0, you don't want it to have a division by 0 error, right? Imagine if this is 0. If you did not add, epsilon is a small value. Epsilon is a small value, which is there not to ensure that there is no division by 0 error, right? So this is where you got your xi hat. This whole step, these 3 steps are your simple data normalization. So what batch normalization does, in addition to simple data normalization, is it says, take each of your xi hats, multiply them with gamma, add them with beta. So this is called scaling and shifting. This is called scale because you're multiplying something. This is called shifting because you're adding something. And what batch normalization says is that I will learn my gamma and beta through backpropagation. Okay, because I can do this with backpropagation, right? Because remember, this whole thing, this is differentiable, this is differentiable, this is differentiable, and this whole function is also differentiable, which means batch normalization as an operation is differentiable, right? Batch normalization as an operation is differentiable. Once you can have it as a differentiable thing, you can make it like an activation unit, which means you can add it as a layer. You're adding it as a layer with 2 parameters, and you will learn your gamma and beta just like your weights. So a batch normalization layer, it could so happen that your gamma is just 1 and your beta is 0. It could happen. I'm not saying this will always happen. If gamma equals to 1 and beta equals to 0, then your xi tilde is equal to xi hat, which means you're just doing simple data normalization. You're doing simple data normalization. The only difference with batch normalization is batch normalization has 2 parameters, which are gamma and beta, which are learned because you can learn it, right? Because the whole batch normalization layer is differentiable, because computing the mean is differentiable, variance is differentiable, this operation is differentiable. This is simple addition and multiplication. So this is also differentiable. As long as something is differentiable, you can add it as a layer and make it work, and you can have parameters to it and make it work through backpropagation algorithm. The only requirement for backpropagation is that you should be able to compute gradients or you should be able to differentiate things, right? So this is the core idea of batch normalization, and it works really, really well. Couple of major advantages with batch normalization. The major advantages with batch normalization is it helps you have faster convergence. It helps you have faster convergence. The reason being, because for any neuron, even in like layer 5, because the inputs are always normalized, inputs are all coming from same distribution, because your inputs are guaranteed to come from same distribution. Imagine, because I added a batch normalization here, the input to this neuron is guaranteed to come from same distribution every time. And when such an advantage occurs, you can afford to have a larger learning rate. So you have your eta, right? The learning rate in the update, if you recall. So wkij new equals to wkij old minus eta times derivative of loss function with respect to this. This eta is what I'm talking about, the learning rate. Because all your inputs come from same distribution, you can afford to have larger learning rate, which means you're going to converge faster. Because your new and old will be farther away. If eta is large, right? If eta is large, your new value will be slightly more away from your old value, which means you're converging faster, right? The second thing here is batch normalization also works as a regularizer, as a weak regularizer. I should call it as a weak regularizer, not a very, very strong regularizer. But you should use batch normalization in addition to dropouts. Please don't skip out dropouts for regularization. Dropouts do very good regularization. Batch normalization also has tendencies to behave like a regularizer. The most important idea here, it avoids internal covariate shift. Internal covariate shift. When you avoid internal covariate shift, you can train deeper neural networks. This is the core idea of batch normalization. Very, very interesting idea.